Welcome to GTC and thank you for joining us today. Before we begin, we wanted to cover a few housekeeping items. At the bottom of your screen are multiple application widgets you can use. All the windows on your screen are resizable and movable. If you have any questions during the webcast, you can submit them through the Q&A window to the right of the slides, and we'll try to answer these at the end of the event. A copy of today's slide deck will be available in the GTC session catalog. You can find additional answers to some common technical issues located in the Help widget at the bottom of your screen. An on-demand version of the webcast will be available approximately 1 hour after the webcast and can be accessed in the session catalog. Now, without further ado, we'll turn the event over to our speaker to begin the presentation.
Hello and happy GTC, everyone. Welcome to AI at Scale in the Real World. 3 reasons your AI will fail and how to overcome. We're going to share 3 secrets on how to make your machine learning better at scale in the real world. I'm Dr. Joshua Sullivan, and I'm joined by my friend and colleague, Dr. Arash Rahnama. I lead the AI software company Modzy, the commercial enterprise AI platform that enables secure deployment, discovery, and management of machine learning at scale. Arash leads Modzy Labs, the heart of innovation at Modzy and source of many peer-reviewed papers and talks in machine learning conferences such as CVPR, KDD, NeurIPS, and ICML. We spent years working to get machine learning systems from the lab and from our development environments into production where they can actually be useful at scale. And we have some great real and practical experience to share with you. We're going to go into each of these 3 areas with some top-line business perspectives, but we're also going to show you real examples, including technical details and how we use NVIDIA GPUs for some incredible accelerated computing. So there's something in this talk for everyone. Now, the harsh reality is this. Many AI models look great in the lab, but they break once you try to deploy them at scale. So we want you to know that's actually pretty normal. It's impossible to plan for every situation a model is going to encounter. And models in production often behave in ways that models in the lab will never experience. You know, after all, the real world is messy and it's complicated. Our experience has shown that 3 things will speed your adoption of machine learning and reduce your risk of failure. 1, monitor for model drift and know how to use it to your advantage. 2, create adversarial defenses. And 3, have a go at explainability. And when used together, you will have the best possible machine learning models out there. So propose something to you. There's a better way to train and inference. Instead of thinking about the 3 areas that I just talked about in machine learning as independent problems to solve, think about how you can have them work together to make your machine learning better at scale. So here's our first secret. Drift and explainability show how a model behaves, which can be used to train robust models that are more trusted, more reliable, and hardened against adversarial attack. So let's see how. First up, model drift. So how do you continuously monitor your model's performance in production and measure the reliability of its predictions? Now, most drift solutions today that you're going to see out there are focused on monitoring the distribution of model outputs compared to some baseline, right? And so outputs is the key word there. These output-based drift detection methods, usually they try to get a sense of the type and frequency of predictions made by the model. And they see if those predictions are changing over time. Now, this usually assumes that these changes are happening because of drift. Now, this is obviously not the best solution because you could be seeing prediction error or error combined with the possibility of drift in data. So in other words, the algorithm may think it's detecting drift in its output, but what you're really seeing is simply prediction error, especially If classes to which the inputs belong have changed due to environmental reasons, so think about this example. If you have a traffic sign detector on an autonomous car, the frequency of traffic signs detected in a dense city is going to be very different than what's observed of traffic signs when the car is driving on the open highway. So that change is not due to drift, but it's due to the change of environment. So this gets complicated. So how do you differentiate simple input changes from actual drift? And what if the sensors you're using to gather telemetry on your model change? How do you detect drift in the data, in your input data, in an unsupervised manner, and do that independently from environmental changes? This is where Modzy's drift detection algorithm can help you. So Arash, it's a very powerful concept of drift detection to include monitoring inputs in an unsupervised manner. Can you show us how we can detect drift in data and use that detection to make better models?
Hi everyone, my first demo today for you is on our solution in regard to drift detection. This is Modzy's approach to detecting drift in input data points. Please let me first explain what drift means in this context, and then I can show you some examples. When we train our AI models, we're usually training them on a training data set that we have access to, and then we test the performance on the test data set to have an idea of how this model will perform once it's deployed. But obviously over time, there's this detachment between the type of data that the model was trained on and the type of data that the user is sending to the deployed AI model for inference. So in other words, your AI model is a function of the data that is fed to it. And over time, as the way we gather data changes, you can think of, for example, if you're having an image classifier that's being run on images captured by specific sensors. If those sensors change over time, then the data has changed, and that means that the performance of your AI model may not be as expected. So this is why you need to design an approach to detect drift, or that difference between types of data over time, so you can have an idea of how reliable your predictions are. So that's the whole idea behind data drift and how drift detection works. It's a necessary part of any AI model deployment process. You have to have a drift detection so you can have an idea of how reliable the predictions you're receiving from your AI model are. So here at Modzy, we have developed this unsupervised approach. So we look at the input data sent by the user to our AI models, and we try to estimate a similarity score between what the data received during deployment looks like in comparison to what the model was trained on. In other words, we want to measure how familiar our AI model is to the data received during deployment. So when we make predictions, for example, for an image classifier, we classify an image into a specific category, and we say we're confident that this is a picture of a cat, for example. We also report another score that you can think of it as a measure of reliability. We tell the user we are this much confident in the prediction we just made. And over time, as more data is sent to our models, the more reliable our predictions are. So you have an idea of how much you can rely on the predictions, and at the same time have an idea of whether you need to retrain that AI model, whether you have to go back to the lab, create a new training data set, and retrain your AI models. So here, what I'm going to do, I'm going to take one of our image classifiers trained on ImageNet, a very famous architecture called ResNet 50. It's trained to classify 10 different classes coming from the ImageNet data set. And then I'm going to test this model against different types of data sets One of them is lower resolution, same 10 classes, but much lower resolutions. One is 2 different classes, but the resolution of those inputs are from that data are closer to ImageNet. And then we have a case where we're testing our base classifier against a data set that's entirely different, no overlapping classes. This is the logos data set. So an entirely different data set. I want to see how we can, in a way, visualize drift for this example, and then showcase our drift detector and show how in an unsupervised manner you can actually distinguish between the types of inputs that your model is receiving. So here's an example of what the model was trained on. So this is our ResNet 50 ImageNet model trained on ImageNet for these 10 different classes that you see on your screen. And then I'm going to visualize the other data sets. So this is our CFAR10 data set. This is data set number 2. And these are lower resolution images that are going to be sent to our AI model. Obviously, there must be some drift happening here. The resolution of the images are different. This is not what the model was trained on. So it's a good test case for us to see what those differences are. This is our 3rd data set. This is the one where the classes are entirely different. So there's no overlap between what the model has seen during training and what's being sent by the user to the model during inference. And the last one is a Kaggle data set. There are 2 classes, dog and cat classes in this case, which are also classes that the model was trained on. And the images are coming from different data sets, but the resolutions and the looks of them are very similar to what the model is familiar with. First thing I'm going to do, I'm going to run this code here, and I'm going to show you the distributions of these data sets. So here what you see what the model was trained on, which is, let's call it ImageNet 10 train and ImageNet 10, which is the test data set. So you have a trained data set, you have a test data set in the lab, you've trained your model, and then you plot the distribution of the features that the model learns from the training and test data sets. There's a lot of math going into creating these distributions. I'm not going to go over them. But here you see that when it comes to the train and test data set that the model is familiar with, those distributions are closely following each other, which tells you that the model learns features in a similar manner. They are very consistent across different input data points. It's what you would expect. This is what you use for training, and this is what you use to estimate the performance. This may work nicely in the lab, but as you see, when I plot the distributions for the test data sets during inference that I just showed you, you see a difference between those distributions. So for example, if you look at this red distribution in this graph, which comes from our lower resolution data set that I just showed you, the CFAR10 data set, you see that there is a big difference between the type of features that the model is learning during inference when new images are sent to it and what it's supposed to learn in a sense. Same thing happens with the logos data set. This is the data set where there were no overlaps between the classes and what the model was trained on. You see that this green plot right here is completely different from what the model is supposed to learn. And then the third case is the Kaggle data set. The means are the same. There is some similarity there, but there's still some deviations between the distribution of the features learned by the model during deployment and what it's supposed to learn. And then I'm going to take these 3 data sets and 4 with the test data. So I'm going to run them against our drift detector. What our drift detector does, it takes the model, ResNet 50 model baseline. It takes the new data set, hypothetically sent to the model during inference after deployment. And it tells you how much it thinks the data set is different from the data set that the baseline model was trained on. And you can see the results here. So when it comes to the train and test data set that the model was, the train and test data set that were used to develop the model in the lab, you see a high confidence score that says, oh, they're the same distributions. When it comes to the lower resolution one, you get the predictions that no, there is drift happening, and there's our approaches or our algorithm is 83% confident that this is the case. Same happens with Kaggle in this case, because the classes overlap and the images are high resolution in the same domain. The result is that we don't think there is a drift happening, and we're confident 80% that this is the case. As you can see, in both cases where there is no drift detected by drift detectors, in both cases, in the case that the drift detector is getting tested against the test data set, train data set, there's a high confidence associated with our predictions, as opposed to Kaggle, which is a new data set, but still is similar enough to the training data set. And then the last one is the logos one, where we again see that there is a drift happening, and and the user should not probably rely on the predictions received from the image classifier. So this is my demo on our drift detector. It's important to mention that there is this need for retraining AI models. There's this need to monitor drift when you deploy your AI models, and it's a natural event that happens when you deploy your AI models. Your AI models should get updated. They should get retrained over time during inference. And it's good to have a way of analyzing that, so you know when the time is for going back to lab and retraining your AI models. There is always this distance between the type of data model is familiar with during training and the type of data that users send to the model. And it's good to have a measure of that difference, and it's good to use that to, over time, retrain AI models and improve their performance.
Thanks, Arash. It's powerful and so awesome to see that in action. Those performance benchmarks that you just showed really demonstrate just how quickly and how far models can deviate from what we want them to be doing. It really also underscores the fact that we need an easy way to both monitor and detect drift so that we can ensure models and productions always remain at that peak performance. Okay, next up in our experience getting machine learning from the lab into the real world is a way to robustly train models. Now, I have to tell you, crafting custom poison data to send to your machine learning model during inference is actually pretty easy. If we want to blind your model so it makes wrong predictions, maybe that takes a couple hours. Model stealing, pretty easy too. Gradient-based adversarial attacks are the easiest thing out there, but there are many ways to attack a model in production. So how do you protect yourself? Well, the answer partially lies in how you train, not just how you inference. Not only do we need to make sure our models do not overfit to training data, but we also need to guarantee that our models don't overfit to input features. This means a model has to make predictions based on the context of the input it's getting. All the possible input features that a model can learn from the input. Then, and only then, does it really become hardened against an adversary. It makes it harder for someone to fool the model by changing only a few input features or pixels if it's an image. So unfortunately, this is not the case for most training algorithms today, and this is why a lot of adversarial attacks exist, because people aren't thinking about this during training. Now, at Modzy, we've developed a way of training which deals with this issue, and we're going to share it with you right now. How do you train your own robust models? This is our next big secret. Arash, we've written several peer-reviewed papers for CVPR and KDD. I know we have a new paper on deck at AAAI on this topic. What can we show to everyone about adversarial defense in the real world?
My second demo today is to showcase our adversarial defense solution. Let me first tell you some about what adversarial machine learning is and what we mean by our adversarial defensive solution. So a couple of years ago, a group of smart researchers figured out a way to fool deep neural networks. And it was surprisingly easy. There was this mathematical way of figuring out how you can add some engineered noise into the inputs received by the AI model, which then in return can easily fool the network. So you can add the input, you can add some noise to the inputs and then make the AI model predict incorrect classes or make wrong decisions. This was obviously an issue because when you're thinking about using AI in real cases or real applications, you want to make sure you can rely on the prediction. You want to make sure there is no chance that someone can hack your system. You want to be able to rely on those predictions. So this is the reason why the field of adversarial machine learning started. How do you design AI models so they don't get hacked, basically? So this is also related to the way we are training our AI models. So why does an AI model get fooled so fast and so easily? Main reason is that the way we are training our AI models today is, in a way, only focused on prediction accuracy, which means I usually send the training data to my AI model, and I tell my model to learn how to predict the classes of these training data points. The problem with that is that when you are only optimizing for prediction accuracy, you're not optimizing for learning itself. So we don't actually teach our AI models how to look at an image and then decide what class it belongs to. We don't tell our AI models how to learn the different features presented in the image, and then based on all the features that it's learning, make a prediction. We just tell our AI model to look at an image, look at a couple of pixels, and then just make a prediction fast and make it correct. So what we've done at Modzy Labs is to develop a new way of training. Here, what we are doing is we are not only training our AI models to make correct predictions, we also enforce or encourage our AI models to learn as many features as possible from the input data. And then after learning all those features, make the final prediction. In a way, we're trying to imitate the way our eyes work. We look at an image and then we learn something from it and we make a decision whether there's a cat in the picture or a dog or a house or a car. But the way we make that prediction is usually based on the context, environment, objects in the image. So we have developed this solution so that our AI models imitate the same behavior. In return, this makes our AI models more robust against adversarial attacks. So our adversarial defensive solution is a new way of training that both improves performance and robustness, but also at the same time can deal with adversarial attacks. So let me show you an example here. And the example here is that you can think of it as, let's say you have a driverless car and it's driving on the road, and you have this image classifier placed on the car that is classifying every single car or object passing the autonomous car. So in this case, you can think of this image as a simple input to this image classifier, and then the object class is obviously sports car. So this is, and then your autonomous car, the control systems within the car use this information to drive the car, basically. Obviously, if this classifier gets hacked by the adversary, there are both security and safety issues associated with that. So what I'm going to do, I'm going to take this image classifier placed on this autonomous car, and I'm going to test it against adversarial attacks. I'm also going to take the Modzy version of the same model and test it against the same attack. And you can see how these two behave differently. So here, what I'm doing by running this function called initialize attack, white box attacking two different models, the basic image classifier and then the Modzy's image classifier. And what happens here, the adversary is looking at each of these two models. It looks at its weights, the architecture, and then it creates one adversarial example for each model. And the adversarial example is really the original image you see up here, but a couple of pixels changed. The insidious thing about these attacks is that what the changes are really small. Now, I'm going to show you the adversarial image, but the changes are so small that sometimes it's hard to detect that the input image is actually adversarial. It's not the original clean image. So here you get the adversarial image is created. It's sent to our robust Modzy model, and you still get the same correct prediction as up here. But again, remember that this is on the adversarial input. It's not anymore on this image up here. And then when you look at the baseline model, the top prediction now is that this is a husky coming up to the car in the opposite lane. So obviously the baseline model gets fooled in this case. And let me visualize for you the adversarial image. So this is the adversarial image created by the adversary when we attack the models. I don't know if you can see in your screens, but there are two pixels change here that if you pay close attention, you can see them. Those two pixels can fool your baseline image classifier. That simple change. So like up here on the bumper, you don't see any yellow or white colored pixels because this is the original clean image. But the adversary changes those two pixels down here, and then you get two different predictions. So this is a good example of how these adversarial attacks work and why you should train your models so they're robust against these type of attacks.
Thanks, Arash. That was an awesome demo. You know, candidly, the fact is that these attacks are possible today. And if you're not thinking about building in these kind of defenses proactively, you're probably too late. Platforms like Modzy, which are open architecture, include embedded security and monitoring features to take a really proactive approach to finding and mitigating these kinds of attack. And finally, maybe the most cutting-edge secret we're going to share today for machine learning in the real world is explainability. Now, this is a big one. Modzy has developed an explainability algorithm that can be applied to any type of model that has an input of language, computer vision, or audio. We do have a paper on Modzy.com if you want to see all the amazing math. Now, understanding how your model reasons against real-world data and avoiding these black box operations is huge toward building trust between people and machine learning models. For highly regulated industries, transparency, explainability, auditability are likely required for compliance purposes. Now, I will tell you, no one has fully solved explainability, but there are steps to know what data influence a prediction from your model and how to understand bias so you can use that information to improve your model. Now, in addition to establishing this trust that I talked about between users and technology, explainability can contribute to model redesign, retraining, and general improvements over time. You can actually begin to see biases created during model training that would have been really difficult to see otherwise. And it may actually be affecting your model's predictions during inference. So Arash, start us off on explainability. What do we even mean by explainability? Why is it so slow? And how do we make it faster?
All right, the last demo I'm showing you today is on our AI explainability solution. So we, at Modzy Labs, we used what we learned from adversarial attacks to develop also a solution for explainability. Our idea was that if the adversary knows how to fool an AI model, it surely knows how the model thinks. And how can we utilize that information to actually explain how these decisions or predictions are made by AI models. So obviously it's good. These black box AI models perform usually well, very fast, make fast predictions. But it's good to know why these decisions are made, or what features in the input contribute to a specific prediction, so that you can make sense of these predictions over large data sets, but also use that information to mitigate bias, or to go back to the lab and retrain your model so it's performing well if you don't like how the model is performing and making its decisions. So here we developed what we call AXAI, which is an explainability solution. And the way I'm going to demo this solution to you today is to just run it against two of state-of-the-art explainability solutions right now used in the AI community. And those two are Lime and SHAP. And I'm going to show you how our approach is faster than both. So in a way, we've developed the fastest solution in the AI community when it comes to AI explainability. And then I'm going to just show you how, at the same time, we're faster than Lime and SHAP and other algorithms out there, but at the same time, we're producing the same consistent results, the same explainability results. So we are giving you what you need to know about how the model is making its predictions, but much faster. If you want a baseline in terms of speed, on a single GPU Tesla V100, our architecture, our explainability tool takes only a second to produce an explainability solution. Lime and SHAP are up to 4 or 5 times slower using the same benchmark. So let's do this. I'm going to run our model. This is, again, an image classifier trained on ImageNet. It's a ResNet 50. And I think in this case, we have an image from Rooster class. And then we're going to visualize where there you go. You can see how the model is making its predictions. So the model is predicting, hey, this is an image of a rooster. So that's my prediction. And then you can actually visualize on the right which part of the image the model is looking at to make that prediction. And then I'm going to run the same input and same model, but I'm going to use Lime this time. And you can see how much slower the solution is while giving you the same explainability solution. One of the good things about our approach is that it can be applied to any type of input and model. So you can apply our approach to NLP models, audio-based models. I'm gonna wait for Lime to produce the results, but at the same time, I'm gonna show you how our approach is run against, let's say, a sentiment analysis model here. So you have a language model, you get a review. It's, in this case, the model is a sentiment analysis model. So it's outputting whether this is a positive review or a negative review. And our explainability solution can look at this entire sentence and tell you why the model made the prediction it made. So in this case, the review says it's a glorified sitcom and a long, unfunny one at that. And the prediction is that this is not a positive sentiment. This is actually a negative review for the movie or TV show. And when you look at our explainability result, you can see that the emphasis is on the word unfunny. So the model looks at that word and then makes a sentiment decision based on it. And then we do the same for audio as well. So a good thing again about AXAI is that you can attach our explainability tool to any type of AI model. Here, in the case of a voice recognition model, you can actually visualize what timestamps or time in terms of seconds and frequency ranges are the most important thing in classifying a specific word in an audio signal. Let me go back and see if Lime is, okay, we're still waiting, close enough. So this is, again, I want to run the same example with Lime to show you how you get the same results, but much faster. We're almost there. So this was our output. This is the explainability result. And this is Lime's result. Yeah, it took hundreds, so more than 2 minutes for Lime to produce its explainability tool, explainability results. And you get the same answer. You say the model is classifying this as a rooster class. And the place it's looking at to make that decision is exactly what we pinpointed in our solution as well. And then same happens with Shab. I'm not going to run this one. It takes another more than a minute, and it gives you a similar result. Again, it's very important to have some type of an explainability tool for your AI models because you want to make sense of the predictions that these models make. And at the same time, you want to use that explanation or those, like the way that these models think to improve these AI models, to go back and retrain them, or to use that to mitigate ethical issues such as bias. If you can visualize which features make a model make a specific prediction, then if those features are biased in any way, you can use your explainability tool to pinpoint those features, and you can go back and retrain your model so that you can mitigate those negative effects. So model retraining, model improvement, you need explainability. But just like to establish trust between your users and AI models. Let's say you have a large data set and it's for a specific application, you're running an image classifier on this data set and you get a bunch of predictions. You want something associated with those predictions explaining why the results are in the way that they are, because obviously not all predictions are correct. If they're correct, you want to know why they're correct. And if they're incorrect, you want to make sure you know why your AI model made the decision it made or made the mistake it made. So that like you have, again, a measure of reliability, a measure of trust that you need to establish and you need to have in order to rely on these AI models.
Thanks, Arash. It was so awesome to see that in action. You know, what strikes me most about this is how much faster Modzy's explainability is compared to the current. And we're sharing this with everyone. It's in peer-reviewed papers. It's out there. We've documented and shared so that everyone can benefit from these kind of advances. Thanks for sharing that with us. What strikes me about explainability is not how much faster it is to get to this trusted decision, but even the savings in terms of compute resources just to get those right answers around explainability. So now we've gone through our 3 secrets to getting your AI to work at scale in the real world and the power of NVIDIA GPUs to accelerate all of this computing. In summary, we've walked through a lot of material today, and hopefully you're feeling a bit excited about the opportunities that lie ahead with your machine learning deployment. We showed you 3 big problem areas with machine learning at scale and concrete ways you can solve these challenges and build stronger processes for long-term success in your organization. If you want to learn more, I'd encourage you to visit our website at modzy.com, M-O-D-Z-Y.com. Check out the wealth of resources, the papers, the blog posts. Feel free to follow us on social media for more real-time updates. Thanks to Arash for all the demos, Thank you all for listening. Happy GTC, everyone, and we look forward to your questions.